Welcome back to Statistics. This time we're going to tackle a very important problem that comes up a lot, the old at least once problem. It comes up so much, it's so important, and it's also a little tricky at first, so I decided I'd just separate it out into its own lecture. And it goes like this. Okay, so in any given year, there's a 5% chance that Shirley's shack gets hit by a hurricane. 5% chance every year. Find the probability it gets hit at least once over the next 5 years. Okay, now this, you'll get more out of this if you pause for a minute and just think how you might approach this. How do you think we should approach this? I'm going to give you a few seconds. You might pause. Did you unpause already? Okay, cool. So, it's I'm kind of hoping that you kind of got stuck a little bit, because if you try to solve this problem directly, it's harder than it looks. So I'm going to put a little bullet park here. I'll say, well, you want to get hit at least once, huh? Well, there's more than one way that you could get hit once, right? There's more than one way to get hit once. What do you mean more than one way to get hit once? Well, you might get hit in the first year. You might get hit in the second year. You might get hit in the third year. You might get hit in the fourth year. You might get hit in the fifth year. So look at all these possible things that could happen. But there's even more ways let's put it this way. Where am I? There are, I guess, even more ways of getting hit at least once. And that's what the question is, at least once. When they say at least once, that means it could be twice. I gotta get used to this pen, man. It's so thick. So anyway, at least once. So you could get hit maybe the first 2 years. Maybe the first year and then the third year, right? Maybe the first year and then the fourth year. Maybe the first year and then the fifth year. Or maybe not the first year. Maybe the second year and maybe the fourth year. And there's a whole bunch there. And by the way, you might get hit twice, or 3 times, or you might get hit 4 times, right? And you don't even know which 4 and so on. So I'm just going to put a big, giant, etc. right there. So there's lots of ways to do this. So it gets complicated. How are you supposed to keep track of all this, right? So here's the tip. What you do for these problems, and it's true of all of these at least once problems, come in by the back door. And what I mean by that is consider the complement. Ask yourself. They want hit at least once. Well, ask yourself, what is the complement of hit at least once? Remember, we were looking at complements in the last lesson. Complement of hit at least once. Well, the immediate way to get a complement is to just put the word not in front. So it's not hit at least once. But then you want to think about, what does that mean if I'm not hit at least once? If I'm not hit at least once, I must have been hit not at all. Not hit at all. And if I wasn't hit at all, another way you might say it is, the hurricane missed us 5 years in a row. 5 misses in a row. Now this is amazingly helpful because it's easy to figure out the chance of getting missed all 5 years. There's only one way to get missed all 5 years, and that's a miss. There's only one way to do it. So in any year, we said there was a 0.05 of getting hit, so probability of getting hit is 0.05, which means the probability of getting missed instead would be the complement of that, 0.95, right? So in any year, it's a 0.95 that you get missed. And then we can do this, 5 consecutive misses. This is the multiplication rule that's going to come up here, right? So this is where you do the old 0.95 to get missed the first year, 0.95 to get missed the second year, 0.95 to get missed again the third year, 0.95 to get missed again the fourth year, 0.95 to get missed again the fifth year. And of course the shortcut way, if you don't want to write that out 5 times, is just to say, well, it's 5 times in the row, so 5th power. Anyway, you ask the calculator and you end up with 0.77378 or so. I guess we could round that to about maybe 3 decimals is good. 0.774. So it's a 0.774 that you won't get hit at all. So, but we don't want that, right? But not that. So I'm kind of uncomplimenting. I don't know what I'm doing. But not that, and so I go 1 minus 0.774, which is about 0.226. So it's a 22.6% chance, probability of getting hit at least once. Because again, this is, I never, ever, ever got hit. Well, the complement of that is you did get hit. And we're not even saying how many times. It's just you did get hit. Maybe once, maybe twice, maybe all 5 times, whatever. So it's the probability of hit at least once over 5 years. Over, I'll say, next 5 years. So do you like that? As Vincent van Gogh might say, what happened? What happened? And if you don't know what I mean, look up Vincent van Gogh on your Google or on your YouTube, even better. Anyway, well, what happened was they asked us one thing, right? They said, hey, get hit at least once over the next 5 years. And what we did is we said, wait a minute, let's think about the complement. So the complement of getting hit once is getting missed 5 times in a row, right? Because if you're not hit at least once, then you are missed every single time. You never got hit. And then that was easier to calculate because you say, well, I'm getting missed as a 0.95. I'm getting missed 5 times in a row. Boom. But again, it's not that. It's the complement of that. So you go 1 minus that answer. Bada boom, bada bing, you're done. Now, isn't that cool? This is a nice method. It's got a few steps to it, and you got to keep track of what you're up to and all that stuff. But it really is a powerful method once you get used to it. So we're just going to do 2 more examples just to really kind of try to internalize this. If you think you're ready already, you might want to pause and try this one yourself. Otherwise, we can start doing this right now. What do we got here? Quincy, the QC technician. He says, hey, 99.9% of the light bulbs coming off my assembly line are up to snuff. I'm going to call those good light bulbs. 99.9% are good light bulbs. You get a shipment of 1,000 of these light bulbs off of Quincy's assembly line there. Okay, cool. So I got a 2-part question here. So the first part is, how many defective light bulbs would you expect in this shipment? So, well, they're telling us that we expect, this is QC talking, 99.9% are good. Well, if 99.9% are good, then the rest of them must be not good or bad. And 100 minus that is 0.1% are bad or defective. I'll just say bad. It's easier to spell. So 0.1% are bad. So in a shipment of 1,000, here's the question. We expect 0.1% of the shipment to be bad. And how do you find 0.1% of 1,000? This goes back to like lecture 2. You turn the decimal into a percent, which means slide the decimal back 2 places to the left, right? Decimal percent. So if you got the percent, you go that way. 2 places, always 2, only 2, exactly 2, never more, never less, 2 places. 0.001 of means times 1,000. And if you multiply 0.001 times 1,000, you actually get 1. We expect 1 bad bulb. I should put the word here. Expect 1 bad per shipment. Now remember, the way the probability works is we're not guaranteeing that there's exactly 1 bad bulb. We're just saying that we expect, on average, over the long run, if you keep getting shipments of 1,000 and you do this over and over like 1,000,000 times, on average, there'll be 1 bad bulb per shipment. Okay, that's what that says. That's question A. So that's a straight percent problem, percent question. Question B, though, what's this say? This says, what's the probability that at least 1 of the bulbs is bad? See, there's that at least 1 thing. At least 1 is bad. Now, we got 1,000 light bulbs. I guarantee you, you do not want to do this. Let's see, the first one was bad and the rest, 999 were good. Or maybe the second one was bad and then 998 were good. Or maybe it was the first second, third, and fourth that were bad. And okay, there's way too many possibilities. We're not going to take the direct path at all. Even if I had Excel, I wouldn't want to take the direct path. So we do the backdoor method, right? So here we go. Backdoor. Give me blue. Give me blue. Give me blue. Okay. The backdoor. So we ask, what is the complement? This is your standard procedure. Whenever they say at least one, standard procedure. First thing you do is you say, well, they want at least one. So I'm going to ask, what is the complement of at least one? The complement of at least one, again, would be, I'll say it's not at least one. So if it's not at least one, it's none. If you don't have at least one, you must have none, right? So I'm going to put the word none are bad. And if none are bad, that means all 1,000 are good bulbs. You open up the box, you test one bulb at a time, you say, that one's good, that one's good, that one's good, that one's good. Try to imagine doing that 1,000 times, and every single time it was good. Wow, what's the probability of that happening? So the probability of all good would be, okay, wait a minute. He said the probability of good was this, 99.99%. So that would be a 0.999 that any one particular bulb is good. 1,000 of them in a row. Okay, aren't you glad we're not using slide rules these days? Okay, so 0.999, let's raise that to the 1,000 power, I guess. And what do we got here? I got a 0.367,695. I have a habit of writing 6 decimal places, or I should say, well, yeah, 6 decimal places, sometimes 6 digits. And then rounding later, but I don't want to round right now because I'm not done with the problem right yet. So 0.367695 is the probability that all are good, but not that. We don't want all good. We want the complement of that. We want at least one is not good, at least one is bad. So 1 minus that 0.367695. And if you do that, you end up with like 0.632305. Now I like to carry decimal places, especially when I'm in big, long, complicated calculations. This one's not so long. But now that we're at the end, I can round off and say, what would be a good place to round? How about if I round to 2 decimal places? I'll make it a percent, which means slide this over twice. And then, did I say 2 decimal places? 1 decimal place. 63.2% chance that at least one is bad. So that's more than 50-50. So if they ship you 1,000 bulbs, it's more than 50-50 that you'll get one bad. Okay, I'm going to stop and summarize this method here. In other words, the first thing we do is we recognize that this idea of at least one bad or is the complement of, you say, not at least one bad, none bad, which is the same as all good. And that's easier to calculate. So then you calculate the probability that all 1,000 are good. Which is the multiplication rule for independent events, right? It kind of means drawing with replacement. No, it doesn't. It's independent because each bulb is independent. That's why it's not, I'm not drawing with replacement. I'm checking each bulb and I'm putting it somewhere. Anyway, independent events is true. Multiplication rule for independent events, and then you go 1 minus that answer because you complemented it, right? In a math way, not complement with an I, but complement with an E. You complemented it. Okay, cool. Right? What is the complement? It's this. Calculate the complement. It's this. I don't want that. I want 1 minus that. That's how it goes. Okay, hopefully you're starting to say, okay, I'm catching on here. I'm picking up what you're laying down. So this next one, example 3. Oh, by the way, this has a typo in it. So before I forget, I forgot to give it a very important piece of information. But let's look at this example here. Donna at the DNR. She's sampling beaches to see if they have E. coli, because if they do, they got to shut down the beach. Since hardly any of the beaches test positive, she has a trick. She combines 5 samples before testing because she's not expecting it to come out positive. So if it doesn't, she can say, hey, I can cross off 5 beaches in one swoop. So that's her shortcut. So what's the probability of it testing positive? Well, the part I forgot to tell you was, so it says hardly any of the beaches. Okay, but how many? So please add this. When she says hardly any, what she means is only 0.5% of beaches are infected. How do you want to say this? Will test positive. Let's put it that way. That's a positive symbol. Only 0.5%, 0.5% of beaches have the E. coli at this time of year or whatever. And so she's like, that's hardly any. I'll just combine 5 samples. And if the sample comes up negative, which I fully expect most of the time, I can say, boom, I did 5 beaches all at once. I'm a happy Donna at the DNR. Okay, so this problem, even though people can figure out the first 2 problems, sometimes they get stuck on this one. So for that reason, pause and try it yourself. See what you get. See what you do. And now that you're unpaused, let's look at this. So here's the question. What is the probability of a combined sample testing positive? See, sometimes you have to kind of rephrase the question so that you get words that are more familiar, that are more like other examples you've done, right? A combined sample testing positive. Well, your combined sample is made up of 5 individual samples. 5, right? 5. So there's 5 individual beaches. So she takes all 5 of those samples, 1 from each beach, puts them together and calls it a sample, right? Now this combined sample will test positive. Let's write this out. The combined sample tests positive if any of the samples are positive, right? You don't have to have all 5 positive. If this beach is positive, the whole mixed sample is going to be positive. Or if this beach is positive, or if these 2 beaches are positive. You get the idea. Any any one. In fact, how about we say at least one? At least one is positive. That's what we're looking for. The probability that at least one is positive. What is the probability of a combined sample testing positive? It's the same thing as asking, what's the probability that at least one of these came out positive? So now we can rock and roll. So let's get rid of some of this highlighting here. So let's see now here. Maybe I'll break into a new color as I keep working through this problem. So you see the at least one show up? That should be like a Pavlov dog response. I just rung the bell. You're supposed to salivate now and say, oh, at least one. I should ask what the complement is. So the complement of at least one is positive, is not at least one is positive, right? Just put the word not in front first. Not at least one is positive. And then after you've put the word not in, try to rephrase it a little more naturally. Not at least one. That would mean none, i.e. none are positive. And another way of saying none are positive is all are negative. That we can do. So the probability that one test is negative, we figure out by using this piece of information that was missing at first. 0.5% of beaches are positive. So that would mean that 99.5% are negative, right? The rest of them. And that would actually, as a decimal, decimals are what we really want when we're calculating things, 0.995. So the probability that one test is negative is 0.995. The probability that all 5 tests come up negative, well, you'd have to do the 0.995 5 times in a row. So just raise it to the 5th power. Grab grab out your button pushing device here, whatever you call this, 0.995. When are they going to install these in my eyeglasses? I want to know. 0.995 to the 5th power is, and I'm getting like 0.975249. I'm rounding to 6 decimal places. Well, not that. We don't want all 5 to be negative. Well, we do really, but we're looking for the chance that not all 5 are negative. So you go 1 minus the 0.975249, and you end up with a 0.024751. We're at the end of our problem. Time to round. I'll make it a percent by moving over twice and saying, I don't know, how about 2.48%? Or in this case, it might be easy enough to just say, hey, 2.5%. 2.5% of our combined samples are going to have at least one bad one. So it's not going to happen much. It's not going to happen much. But let me ask you, what happens if it does? Let's say we get a combined sample and it comes out positive. What do you do next? Well, what do you know? What you really know is that at least one of these has E. coli. You don't know which one. You don't even know if it's 2 of them or 3 of them. It might be all of them. It doesn't have to be. So what you'll have to do to figure out which one is you'll have to go back to those 5 beaches and you'll have to sample them all individually and see which one or which ones are positive. Okay, so it's a little more work, but most of the time, 97.5% of the time, it's going to come up negative, and you're going to say, well, that takes care of those 5 beaches. That takes care of those 5 beaches. So in the long run, this really is going to save you a lot of work and a lot of money. Tests cost money. So it's a good idea, and they really do this. So if you go and get tested for HIV, they'll probably say, hey, if we call you back and say it's positive, don't worry. It just means that you have to come back and get tested again. Because they combined a bunch of samples, and all they know is that somebody has it. They don't know if it's you, so you have to go back and get tested again. So if you've ever had to get tested for anything, HIV was a big scare way back when, so we all got tested. Kind of like COVID nowadays. Everybody had to get tested, right? So anyway, I don't know if they pull those samples. Maybe they do. Anyway, at least one. It's what's for dinner. Oh, a 22-minute lecture. That is a record.